Let's review inductance. Remember, an inductor is just a coil of wire wrapped around some core. The core could be air, so there may not even be a core material, in which case this would just be a coil. So it's a pretty simple construction. However, there are a few factors that affect the amount of inductance in our circuit, or the self-inductance of the inductor. One being the number of turns, or the number of coils, the length of the inductor, the material of the core, or the permeability, moreover, of the core material, or how easily that material can be magnetized, and then the area of the coil itself. So in this case, we have a 10 microhenry inductor here, and we're going to keep the area the same. We're going to keep the core material the same. Looks like it's air here. And we're going to keep the length the same. The only thing we're going to do is double the number of turns. So in our equation, the number of turns is squared. So if we keep this the same, that's a 1. If we keep this the same, that's a 1. If we keep this the same, that's a 1. However, n becomes 2 because we're doubling the number of turns. So essentially, it's like we're multiplying the number of turns by 4, because 2n squared means that we've got a fourfold increase in the inductance. So 4 times 10 microhenries, that would be 40 microhenry inductor here, just from doubling the number of turns, because it's squared in our equation. So if we had tripled the number of turns, we would multiply this by 9. If we had 4 times the number of turns, we would multiply the inductance by 16, and so on. Let's look at another change here. So we have a 10 microhenry inductor that we're starting with again here. This time we're going to triple the area, half the number of turns, and then keep the air core and keep the length the same. So we're changing two things this time. So in our equation, we're going to put 1/2 here, so we're squaring 1/2. So that means basically multiplying it by 1/4. And the area is tripled, so we're multiplying it by 3. So it's essentially multiplying our 10 microhenries by 3 times the area over 4, because we're halving the number of turns. So we would have 7.5 microhenries for our second coil there. Here it looks like the changes we're making, we're substituting the air core for some other core material that has a much higher permeability, 1200 times actually. We're increasing the length by 2.5 times. We are tripling the number of turns, and we're keeping the area the same. So in our equation, that means we're multiplying this by 1200. We are squaring the 3, so that's times 9. Area stays the same, so that's like a 1. And then the length is 2.5. So basically, we have 1200 times 9 divided by 2.5 times the 10 millihenries we started at. And that gives us 43.2 millihenries of inductance here. So almost a little over 4 times the amount of inductance from making those changes. The storage and release equations for the inductor you will not have to write for the final exam. However, you do need to recognize what's going on with the current. For instance, remember the current through the inductor starts at 0, and then as we get past that storage phase, all of the current is allowed to flow through the circuit, and this looks like a short circuit. Whereas the voltage starts at a maximum voltage and goes to 0 during the storage phase. So you do need to know what's going on in the storage and release phase, but I will not have you write the equations for those. Combining inductors, you would do that the exact same way you did resistors. So series inductors you would add, and parallel inductors you can combine just like parallel resistors. So here you've got your 4 Henry inductors in parallel, so that would be 2 Henrys right here. The 2 then would be in series with that 4, so there's 6 Henrys there. That'll give you 6 here in the middle in parallel with 4. So 1 over 1/6 plus 1/4 will give you 2.4. And in steady state, remember, your inductor looks like a short circuit, your capacitors look like open circuits. So the first thing you want to do when you identify that we're looking for this in steady state is replace all of your inductors with a short circuit. Just draw a wire right there, and replace all your capacitors with open, so you would remove those from the circuit. And I would redraw my circuit. Okay, so what you notice here is if we had current flowing through here, there's really no return path to the ground or to the negative terminal. So in that way, there's no current flowing anywhere in the circuit. So I1, I2, both are 0. What does that mean for our voltage drops across those capacitors? If there's no current through these resistors, there's no voltage drop through them either. So V1 is connected to the positive terminal of the source and the negative terminal, and so is V2, because those look just like wires there. So both of those drops would be 60 volts.